Let's take a look at an example in chapter 10. So chapter 10 example. And I want to look at page 310, number 16. Okay, so the setup for this problem is to the idea is that we want to explore if experiencing periods of adversity in your life it influences your overall well-being and or your your ranking of how you're doing. And so they looked at the sample of college students and they split it into two groups, and they said, okay, those who in the last 5 years, those students who had experienced less than two periods of adversities or occurrences of something that was adverse to their life, let's look at their well-being. And so the sample for that was 18. There were 18 students that they asked, and they gave them an average well-being score of 42. I don't know what that means. There you go. And then the sum of squares was 398. Okay, this is for the first group, and this is for only two or less adverse experiences. Okay, they had they had 16 people that experienced more than two adverse experiences in the last 5 years. And the well-being scores for this group, the average was, let's see, the average was 48.6. They gave them a score of 48.6. Maybe this is out of 50, I'm not sure. And the sum of squares is 370. Okay, so what we want to do is figure out if there's a significant difference between these two groups. So maybe I'll pose that as a question. Is there a significant difference between the populations? Okay, so we can start with the assumption that there is not a significant difference. This is the null hypothesis, 0, would be that mean 1 minus mean 2 is equal to 0. Okay, and we don't know. I mean, you can't just conclude that more adversity should give you happiness, and so or overall well-being. And so we're going to run a two-tail test. And so the alternative is that the difference is not 0. And so we're going to do a two-tail for this one. Two-tail test. So let's think about our statistic here. With the data that we have, the t statistic is going to have degrees of freedom. Well, it's going to be 16 plus 18 minus 2, which should be 32. Okay, so 32 degrees of freedom. The mean difference, m2 minus m1, is equal to, let's see here, 48.6 minus 42, which is 6.6. Okay, we're going to assume that the difference is 0 between the population, and so the numerator is just going to be 6.6 for the t statistic. So the t so far looks like this. T with degrees of freedom 32 is equal to 6.6 out of, and then we got to come up with the estimated standard error for the difference. Okay, so recall then that the estimated standard error for the difference is going to be the square root of the pooled variance squared divided by the first sample plus the pooled variance squared divided by the second sample. Okay, and remember then that SP squared is equal to the total sum of squares divided by, degrees of freedom. I gotta erase that. Divided by the degrees of freedom in 1 plus the degrees of freedom in 2. So for us, our pooled variance is going to look like this: 398 plus 370 out of 17 plus 15, so that's going to be 768 out of 32, which gives you 24. Alright, and then the estimated standard error for the difference is going to be the square root of 24 out of, let's see, 16. What's in the first one? 18 plus 24 out of 16, which gives you the square root of 2.833, which is equal to 1.683. So our t statistic with degrees of freedom 32 is equal to 6.6 divided by 1.683, which gives you about 3.92. All right, so what we want to do is the description tells us that we want to do a two-tail test with alpha equaling 0.01. So let's take this information here, our t equaling 3.922, and let's compute the p-value for this. Let's go to a new page, and so we want to come up with what is the probability of observing a t-value that is greater than or equal to our t-value. Okay, and since this has the absolute value, we're going to take it in two tails, and so we're going to say that our p-value, let's flip over here. In our case, it's the probability of t being greater than or equal to 3.922. 3.922, and then we're going to double that. Okay, one of the things that we should point out here, when you have this t statistic, one tail or two tails. So we're looking at two tails, and so we're going to look at the proportion in two tails combined, and so this is the alpha that we're looking at. Okay, we find our degrees of freedom down here, and we see that, okay, well, 32 is not part of it. Oops, 32 is not part of it, but we can find 30. Maybe I'll get that pointer here. We could find 30, and so we go all the way over, and we see that the critical t is 2.750. Okay, so ours being 3.922 tells us that our p-value is going to be less than 0.01, but we won't know exactly what it is. Okay, so one of two things we could do. We could say then our p-value is less than 0.01, and that's all we really know from the table, right? I mean, our p-value is generated by degrees of freedom 2.750, and notice that if you go to 40 it decreases, and so we're somewhere in between those two. And so here, if we're going to actually be greater than this number, that means our alpha, or our p-value, is going to be less than this alpha. Okay, so our p-value is less than 0.01, so that's enough to reject our null hypothesis. So we would say reject HO in favor of H1. In other words, we're saying that adversity does influence well-being ranking scores. I don't know how you want to say that. Well-being scores. Okay. One of the things though that we want to that we need to really compute, and that's this idea of Cohen's d. So the estimated effect size. Before I do that though, I want to highlight this. So our t value for 32 was 3.922. The critical value for degrees of 30 was 2.750. Our t was bigger than 2.750, which this one corresponds to alpha. This one corresponds to alpha of 0.01, two tails. So if we drew a picture of the t, and this is kind of my really not very good drawing of the t. So fat tails. Okay. Here is the critical value, 2.750, negative 2.750. We're saying that in this region and this region, collectively the area is 0.01. Okay, so our t of 3.92 landing way up here, 3.922, clearly, and even if we looked at the negative form of that, negative 3.922, clearly has area that's less than the alpha. Okay, so showing that our t is greater than the critical t, that's enough to reject, or showing that the p-value is less than the alpha, that's also enough to reject. Okay, so our conclusion then, we also have to find the estimated Cohen's d, and so that's going to be given as estimated is going to be equal to the difference in the means, and I'm going to take the smaller from the larger, and then the square root of the pooled variance. And so this is going to be for 6.6. That's the distance. I don't care if it's positive or negative, just the distance from between the means, and then the square root of 24. So that's 6.6 out of 4.899, which gives you 1.347. So our Cohen d then is 1.347. Okay, so our t-statistic, our p-value, and our d is what's important when we make our statement. And so we can say, to answer the last part, to write a statement for this, we would say something like people who experience adversity. Well, how about we say moderate adversity? Because we were saying that they experienced more than 2 adverse events in the last 5 years. So moderate adversity had significantly higher well-being scores. Higher well-being scores. Than those with little or no adversity. Okay, and that claim is, we have to support it, and we put our values that support it, and this is really critical, and also for the quizzes you need to put these. Anytime you reject or don't reject, anytime you make a claim about a hypothesis test, you have to provide this information. And so you make this claim, people who experience moderate adversity had significantly higher well-being scores. In other words, this is the better interpretation than just saying reject the null hypothesis, because it's actually putting in what the null hypothesis meant. So people who experience moderate adversity had significantly higher well-being scores, and we would support this with our t-score of 3.93, place our p-value at less than 0.01, which was the critical value. So in other words, if somebody were to say, well, it's less than 0.01, therefore it satisfies being less than 0.05, they can rerun the test and justify the work. And then we would also put the effect size, the estimated d, 1.347. So that part right there in green is required. So not only do you make your statement about rejecting or not rejecting the hypothesis, you then have to provide the information that allows you to make that claim. Okay. One last thing, I want to go through the computation for r squared. So r squared, again, the percent of variation accounted for is going to be the t-squared value divided by the t-squared plus the degrees of freedom. And so for this test, r squared is equal to, our t was 3.922, 922 squared, divided by that same value plus the degrees of freedom of 32, and so this is going to be 15.379 divided by 15.379 plus 32, which gives us 15.379 out of 47.379, and it's only about 32%. So not very much is accounted for. Okay, and so mainly this is small because our degrees of freedom. Okay, one way to make this effect bigger, not the effect, the r squared to be larger, we would have to either have smaller degrees of freedom, or we would have to come up with a much larger t value. But notice that if I increase it here, it also increases here, and so there you go. Great.